press the bell icon on the YouTube app and never miss another update.
Hello dear students, so let me continue next lecture from work energy power. So anyhow, up to now I covered 6 lectures from work energy power. Now let me continue part 7 from work energy power. Part number 7 from work energy power. Okay. See, anyhow, up to the last part, I covered a motion of a body along a vertical circle with a non-uniform speed. Anyhow, we know the speed of the body at the lowest point of vertical circle and at the highest point of vertical circle. Of course, at some point also we know. So, anyhow, at the lowest point we know V1 we got it as root of 5gr. At the highest point, root gr we are getting. At the some middle point, root 3gr. And of course, I given some shortcut formulas. And we know the difference between the tensions in non-uniform speed case. How much we got? So we got T1 minus T2 is equals to 6 mg. Okay. And in the same way, we know speed of the body in a vertical circle with uniform speed. Uniform speed means everywhere we got V is equal to root gr. Okay, if you rotate a bucket full of water in vertical circle, then the water never come out from the bucket if you maintain speed of the bucket which is equivalent to root gr. Okay, so there are plenty of applications based on circular motion. Anyhow, I covered 1 or 2. Based on the situation, I will cover some more also. And of course, I covered one problem in the last session. That is, a block is placed on a vertical circle, on the track of a vertical circle, and that is given with a speed V0. If it is given with a speed V0, then after some interval of time, the block leaves the contact from the vertical track. Means at what angle the block is leaving. That also we done in the last session. Now in this part 7 lecture, let me cover the next topic from NCERT. So write down the heading, the potential energy of a spring. So write down potential energy of a spring. Potential energy of a spring. So same spring concept will come in some other chapters, that is oscillation and some mechanical properties of solids. Okay. Here generally spring has a spring constant. That spring constant we can represent with some K symbol. This is also called as force constant. Based on this K, we can decide whether the spring is stiff or weak. For suppose if K is high, if K value will be more, if K is more, we say that the spring is said to be stiff, strong. Okay, the spring is said to be stiff, strong. Okay. If K value is less, then we say that the spring is said to be delicate, weak. Okay, weak. So the spring is said to be strong based on the K value. If K value is more, we say that the spring is said to be strong. If K value is less, then the spring is said to be weak. So based on the K, we decide whether the spring is strong or stiff or weak. Here, let me derive the potential energy equation of a spring. Okay. So to derive this, let me consider a block whose mass is m. See, what I am deriving here is, I am deriving potential energy of a spring. To derive this, let me consider a block of mass m. That mass which is connected to the spring. Okay, one end of the spring is connected to the block. Other end of the spring connected to some wall. Okay, some wall. Other end is connected to wall. Just you see the diagram. See, this is the vertical wall. And this is the horizontal surface. Nothing is given means you feel as a smooth. And this is the spring layers. Spring layers connected to the block, whose mass is m. This spring has spring constant k. Spring has a spring constant k. Initially the block is here. So this is the natural length of the spring. Spring is in its natural length, original length. Here, let me suppose this is the initial position of the block. X is equals to something 0. Along x axis, x is equal to 0. If I pull this block away, then what about the spring layers? Definitely there will be a stretching force. So if I pull in this direction, then some layers of the spring will be stretches. So some stretching force is developed in the spring. And if I move right side, this spring will try to pull the block back side. That means spring will apply a force on block. And some stretching force is developed in the spring. That force, call it as restoring force. That force is called as restoring force. Okay, if I apply any force on a duster, then if I remove this force, again the duster will come to the original shape and size because of restoring force set up inside the body. So here also the same thing. If I apply a force right side, spring force, that restoring force I call it as spring force. That spring force will be left side. For suppose, see the next diagram of this one. See, let us suppose the block which is, see this is the initial position of the block. Now the next position is, see this is the next position of the block. And these are the spring layers. Okay. So this is the starting position and this is the next position. Let us suppose this is something x is equal to x. This is x is equals to 0. Then what is increasing? So the block displaces by x. The block displaces by x. So here I can write x is positive because the block is displaces x. But the spring will try to pull this block to the backward. This spring will try to pull this block backward. Means some spring force will be set up here. That spring force, let me write, spring force is Fs. Which side the spring force will be there? This side. This is the spring force for this one. Okay, spring force is left. If x is positive, spring force is negative. Negative x axis. X is positive. How these two? Okay, actually this is done under the application of force. That force is proportional to x. But that force, external force, okay, if I apply any force on here, that is called as generally external. That external force, no doubt, which is equal and opposite to the spring force. External force means that force applied by you on a block. If I applied a force, that force is external force. That external force is, let me write here, external force which is equal and opposite to the spring force. This is spring force. Fs is spring force. Okay. But what about external force? External force, no doubt, proportional to x. If you apply more external force, body undergoes more displacement. F external proportional to x. So F external, remove the proportionality, introduce a constant k. F external nothing but, what is F external? Minus Fs. So minus Fs which is equivalent to Kx, then F suffix S which is equivalent to minus Kx. So this F suffix S called as spring force, and this is also nothing but a Hooke's law that will come in elasticity chapter, mechanical properties of solids, Hooke's law. Okay, that we will see other chapters. Here this is the force law, we can write it as force law. And what is this Fs? Spring force, spring force, otherwise it is called as spring force. And this K, what is K? What is the name of K? I am writing everything now. Spring constant, otherwise we can write it as force constant. Spring constant, otherwise force constant. I got spring force. This is the force law. Actually force law in SHM, simple harmonic motion. But okay, leave it here. If X is positive, what about Fs? Negative. If the block comes in this side, for example, see the next situation. Actually block undergoes some oscillations. So oscillation we have a chapter, separate chapter, we will discuss in detail in that chapter. Here the next position we can expect like this. The spring will compress. Maybe the position of the block is this is X is equals to minus X. Okay. So if the block move back, then what is X? X is negative. What about Fs? This spring will try to pull this block right side. If it is comes closer, this spring will try to pull this block right side. Means what is Fs? Fs positive. Got this thing? X positive, Fs negative. From the diagram only we can understand very clearly. I drawn neat diagrams here. X positive, so the spring will try to pull this block backside. Fs negative. Here X negative. X is negative. Then spring will try to pull this block to the right. Means what? Fs positive. See why I am using these things is, let me draw the graph at the end. That's why I am using these symbols. X positive, Fs negative. X negative, Fs positive. Okay. Now target is to find out the potential energy. During this displacement, of course it is done under the application of some external force, otherwise spring force. This spring force will do some work. That work done let me find. And anyhow, we know spring force is what? Is a constant force or a variable force? No doubt it is a variable force. Okay, variable force means whose magnitude is changes, you know already. So spring force is a variable force. Of course it is a non-conservative force. Okay, non-conservative? Yeah. No, spring force is a variable force right now. Okay, spring force is a variable force, it's not non-conservative. Okay. Now what are the non-conservative forces? Frictional force, viscous force, not spring force, sorry. So spring force is a variable force. We know work done by the variable force. We know that work done by the variable force, I think you remember the formula W which is equivalent to integration of F dx. Anyone remember this one? Integration of F into dx. What is this? Work done by the variable force. Why? Because spring force is the variable force. And here the limits, starting is 0, ending is x in this situation. So 0, this is x, F nothing but Fs. F nothing but Fs, spring force, work done by the spring force. Therefore, W is equals to integration of 0 to x. What is Fs? Minus kx dx. I think you know the integration process. W which is equivalent to minus, let me write k outside, integration of x dx, 0 x. So W which is equivalent to minus k, integration of x dx is x square by 2, after the limit also it is same, x square by 2. So W which is equivalent to minus half k kx square, and this work done by the spring force which is stored in the spring is in the form of potential energy. So this work done is stored, this work done is stored in the spring, this work done is stored is in the form of potential energy. Okay, that can be written as U. U is equals to, I am getting half kx square. So this is the potential energy of a spring. So potential energy of a spring. Derivation generally they will ask for PUC board point of view. That's why I am spending some time. So U is equals to minus half kx square. Okay. So take this, and that work done by the spring force is stored in the form of potential energy in the spring. So that can be represented as U. U is equal to half kx square. Minus I am getting means spring is elongated. If the spring compresses, okay, this is the case I am taking from 0 to x. If the spring compresses, this is the spring elongates. Okay, I am getting, if the spring elongates, I am getting minus half kx square. If spring compresses, we will get opposite. Spring compresses, then U is equal to, you will get half kx square. Okay, generally we will take the magnitude. So half kx square. Take this. Let me extend few things here. Okay, in some other chapters, two blocks are connected to the two springs. Springs are in series, springs are in parallel, spring is cut into some pieces. Okay, that you are going to learn in some other chapters. Okay, here they given in one kg power only this derivation. Let us continue this. See, by using this data, let me plot a graph. If we study this topic in oscillation, definitely we understood something good than this. Okay, in oscillation, some time period, oscillations, all the things will come in oscillation chapter. Yeah. Completed? Yeah. So, let me continue now. Let me rub this. See, this is the case when spring is stretches by some 0 positions to x position. Okay, 0 positions to x position. Now let me plot a graph. Anyhow, spring force proportional to displacement and opposite in direction. Now let me plot a graph. This is something Fs, spring force. Okay, spring force, and this I am taking x. Spring force proportional to distance. If a spring force is positive, what is x? Negative. So you will get a graph like this. Just you check it. Okay, so this is the graph. X is equal to something x. Okay, if x is positive, f is negative, downside. Check it. If x is positive, f. Okay, if x is negative, what is f? Positive. F is positive. Oh, okay, f is positive. So this is the graph. So we are moving from 0 to x, this region only. Okay. And of course we can plot some energy curve also. So energy curve we can understand clearly in oscillation chapter. Energy curve they given in something NCERT like this. So this we can understand very clearly in oscillations. Okay, here okay, leave the energy curve. So energy curve is nothing but, see, this is nothing but mean position, starting position nothing but the mean position. This is extreme position, maximum displacement of the particle from mean position, called as something extreme. Actually that is amplitude we can call. Extreme position, positive extreme, this is negative extreme. So in oscillation chapters you are going to understand that at mean position displacement 0, but there will be some velocity here. Okay, if displacement 0, velocity may be 0, may not be 0, you know that conditions in kinematics. So at mean position, if you feel this as something mean position for you especially, okay, so I know all these things now, but here at mean position velocity is maximum, something energy will be there. If velocity is there, what type of energy is available? So you feel this is the mean position. Okay, it's not a feeling, it's the correct actually, in mean position. So at mean position velocity will be there. As velocity is available means, velocity is maximum means kinetic energy will be maximum. Kinetic energy is maximum. If kinetic energy is maximum, potential energy minimum. Okay, these conditions we are going to derive in detail in oscillation chapter, like some total energy of oscillator. There you are going to get a graph like this. Okay, right now I am drawing the graph directly. So this is the x is equal to 0 position, x is equal to x position, extreme. At mean position you will get a graph like this. Okay, this is potential energy 0. Here at extreme potential energy is maximum, here potential energy is maximum. So this is the kinetic energy curve. Here kinetic energy is maximum, kinetic energy at extreme, velocity is 0, so kinetic energy is minimum, 0. So you will get the same graph in oscillation chapter, so no need to worry at this situation right now. So in oscillation we are going to verify everything. We have some equations, velocity equations, displacement and potential energy, kinetic energy. So there we are going to understand this graph now. So right now just write down a graph. So this is your wish, but you draw this graph. Okay. Now let me extend one more formula in spring concept. Physics is nothing but linked. Okay, some topics are linked with other chapters also. So this is the PE curve, above one is kinetic energy curve. Now let us see one or two points about spring. You take that as a something note point. If block displaces from x is equals to something x1 positions to x2 position, then let us see the potential energy, let us see the work done. Then we can write W is equals to, what is our formula? X is equals to x1 to the x2 fs dx. This is our formula. So apply the integration, you will get the answer. x1 x2 fs nothing but kx, I am writing minus outside, dx. So I think you know the integrations, otherwise not possible here. Minus k integration of x dx, x1 x2, minus k x is x square by 2, substitute upper limit and lower limit. So x1 x2, let me rub this one. Okay, don't worry about this one, you wait up to the oscillation chapter, so leave this one, no problem. So substitute the upper limit, this energy nothing but u minus k x2 square by 2 x1 square by 2. So u is equals to half k 1 by x1 square minus 1 by x2 square. So this is the change in potential energy actually. If the block displaces from x1 positions to x2 position, keep the formula in mind, very basic, half k 1 by x1 square minus 1 by x2 square. Take this. Now see, anyhow at mean position there will be a velocity, okay, there will be a velocity. If v is the speed of the block, in some problems they will give, if the block is moved with a speed v, then what is the elongation in the spring or what is the compression in the spring. So if they given velocity of the block, then let us check. Yeah, I think completed. Easy things, so let me continue now. See, they given block of mass m connected to the spring whose spring constant is k. If block of mass m, if m moves with a speed v, of course starts from rest, okay, indirectly block have some acceleration, uniform acceleration. So if a m moves, if block moves with a speed v, then in this situation the block will have some kinetic energy. That kinetic energy, from law of conservation of energy, that kinetic energy of the block, which is equivalent to potential energy of the spring. So potential energy nothing but, so just we can balance with potential energy, we can balance with kinetic energy from law of conservation of energy. Okay, so this is the kinetic energy of the block, okay, and this is half k x square and this is half m v square. So if they ask you to find elongation x square, which is equivalent to m v square by k, so x is equals to m by k into v. So this is the elongation produced in the spring, elongation of the spring. So x is nothing but elongation, compression or elongation. So elongation of the spring. Yeah, completed. So let me give one small problem based on spring. So write down the question. A spring of force constant k is stretched by a small length x. So write down the question. A spring of force constant k of k. Spring of k means spring of force constant k, okay, is stretched by a small length x. Spring of force constant k is stretched by a small length x. First it is stretched by x. Next what again we will see, x. Then find the work done. Find the work done in stretching it further. In stretching it further by a small length y. By a small length y. So read the problem. Very simple question. This is basic questions. First, initially it is stretched by x. Finally, it is stretched by further means from x onwards he is stretching by y. Nothing but what is the next elongation of the spring? First, it is stretched by x. Next, it is stretched by x plus y. First potential energy, let us consider u1. Next potential energy u2. u1 is half k x square. u2 is half k x plus y whole square. Then they are asking how much work done means just you take the change. u2 minus u1 will give our answer. Right. Simple question. So let me write directly. So the increase in work done or the additional work done. Increase in work done, otherwise additional work done. We can write W is equals to directly U2 minus U1. So W is equals to U2 half K x plus y whole square minus half K x square. Simplify it. Next is second one is x plus y displacement. First one is x. So W which is equivalent to half K you write outside. X plus y whole square minus x square. Therefore, W half k x plus y whole square, x square y square 2xy minus x square. Therefore, W is equals to half k y square 2xy. Let me take y common. It is 2x plus y or y plus 2x. Yeah. Completed. Let us try one more questions about the spring problem. Let me give the proper question so that we will get correct answers. So let me give proper question now. So the question is lengthy, no problem. So try to understand the question now. A massless platform is kept on a light elastic spring. So write down the question. A massless platform is kept on a light elastic spring. Nothing but k value less like that. Spring as shown. Okay, as shown in figure. When a particle of 0.1 kg is dropped, 0.1 kg mass is dropped on the pan from a height of 0.1 the particle strikes the pan and the spring compresses. Then spring compresses by 0.01 meter. 0.01 meter. Find from what height should the particle be dropped to cause a compression of 0.04 meter. So write the question. So write the problem. Okay, let me draw the diagram. So this is also simple question. It's not a tough question. Is lengthy. No need to worry. A massless platform which is kept on a light elastic spring as shown in figure. I am going to draw the diagram. When a particle of mass 0.1 kg mass is dropped on the pan from a height of 0.24 meter, then spring compresses by 0.01 meter. From what height should the particle be dropped to cause a compression of 0.04 meter? Just you see the diagram. So let me draw diagram here. See, this is the particle whose mass is given 0. How much? 1 kg. Is it clear? This one mass 0.1 kg which is dropped from what height? Dropped from a height of 0.24 meter, and it is dropped on a pan. See, this is the pan. Pan is massless. This is connected to the spring. Yeah, this is the diagram. Simple question. It's not a tough. Is spring constant is given? Spring constant is not yet given. So, no problem. Leave it. So, the mass is dropped from a height of 0.24 meter so that the mass touches the pan. Once the mass touches the pan, then what about the pan? Will it move down or not? So, the pan compresses like this. What height it is compresses? What height it is compresses by 0.04. Okay, 0.04. Observe the problem here. Mass is falling from certain height. Nothing but there is a loss in potential energy. Mass is falling from certain height means loss in potential energy. Okay, if it falls from a height of something h, then it will be extended by how much? Sorry, compressed by how much? Y. Then what is the total height of the particle? Total height of the particle h and y, h plus y. So, h plus y. Here, the loss in potential energy, no doubt, which is balanced by gain in kinetic energy, okay, of the spring. Loss in potential energy we can write it as mgh plus something y, which is equivalent to half k x square. Half k x square. What they are asking? At what height? From what height should the particle be dropped to cause a compression of this much? Compression. That y is the compression. Okay, y is the compression. Starting how much it is compressing? 0.01. Next 0.04. Okay. So first it is dropped from 0.24. Then from what height? Height we need to find. Yeah, this is what? It's not x. What is this? Y. Compressed by y. So let us use, here mass is okay given, g constant, half constant, k is not given. Just to use the proportionality, h plus y proportionals to y square. This is enough. H plus y proportionals to y square. K is not given, so leave it. So let me write this one as h plus h1 by y1, h2 by y2, which is equivalent to y1 square by y2 square. So all the values are given here. What is h1? 0.24. y1 0.01. h2 is target. This is 0.04. y1 by y2 whole square. What is y1? 0.01 by 0.04. I like whole square. So this cancel 1 by 4, 1 by 16. 1 by 16. Just you do the cross multiplication. Okay, you do the cross multiplication. This is what? 0.24 plus 0.01. How much it is? 0.25 by h2 plus 0.04. This is 1 by 16. 1 by 16. Do the cross multiplications and get the h value. You will get something 3 point something value. Try to get the h2. Do the cross multiplications. You will get 3.96 meter. You will get, just you check it, 3.96 meter. So I left the calculation to you. Try to calculate it. Here h plus y proportionals to y. Verify the calculations. 3.96 meter. Yeah, verify the calculations. Got 3.96. Okay. Let me give one more problem so that I can stop the spring concepts. Okay, so cutting of springs, springs connected in series, springs connected in parallel, we are going to learn in some other chapters. Now let me give one more problem. So let me write the problem in a shortcut way. See what I am going to find out, that you are try to understand here now. Let me draw the diagram. Better you draw this diagram. They given a spring gun. So this is also somewhat good question. See, this is the spring gun having spring with some ball attachment. See, this is the ball. This is at a height of the given h. This h is given 2 meter. Let me write the data. Yeah. So the question is, let me give the question. So write the question. In a spring gun having spring constant, so having spring constant given, so let me write here shortcut way, given k value, write down k value directly, k is Newton per meter, this is m, let me write the data directly, m is equals to 0.1 kg, okay. Written? So write the question better. In a spring gun, having the spring constant having spring constant K is equals to 100 Newton per meter and mass given 0.1 kg, 1 kg is put in its barrel, is put in its barrel by compressing the spring by compressing the spring by 0.05 meter as shown, 0.05 meter as shown. The ball leaves the gun horizontally at a height of 2 meters above the ground. Okay, the given height. The question is, first one they given, the velocity of the ball when the spring is released. We have to find the velocity of the ball when spring is released. When the spring is released. Second question, where should a box be placed? A box be placed on the ground, so that the ball fall on it, so that the ball fall on it, the ball fall on it. Take G value 10. So read the question at least twice. So let me read. Say they given a spring gun. Having force constant is given 100, mass is given 0.1 kg. That is put in the barrel by compressing the spring by 0.05 meter as shown in figure, and this is at a height of 2 meter from ground. Now target is to find out what is the velocity. Note that this is horizontal velocity. Velocity of the ball when spring is released. If the spring is released, this ball will move with a speed v. Then what is that velocity? And where should a box we have to place so that this ball has to reach in that box? So let us suppose the box is placed somewhere here. This is the some box. So that this ball has to come here. See, this is like a horizontal projectile. I think you know horizontal projectile. There are two types of projectiles: oblique projectile, horizontal projectile. So the ball has to come here. Means first you have to find velocity. And this is the horizontal range. You know this one, range, velocity into time. To find the velocity, here once this ball is pushed, means the spring is pushed. Okay, if the spring is compressing by 0.05 meter, then what type of energy will be converted into other energy? No doubt, there will be a potential energy of the spring converted into kinetic energy of the ball. So we can write directly potential energy of the spring, elastic potential energy, which is balanced by kinetic energy. So this is half k something, if it is x square, which is equivalent to half m v square. Half, then x we can get. X is already given, target is to find out v. So what is v? V square is equals to k x square by m. Then how to get the v? V is equal to root of k by m into x. How much k? 100. How much m? 0.1 kg. X 0.05. Then get the v value. 100,000 0.05. Verify the v. How much v? Okay, see, let me write like this. This is 100. This K is 100, yeah. 100, this is 10 raised to minus 1, nothing but 0.1, let me keep as it is. 0.05, 5 by 100, 5 by 100. Okay, do the calculations. This can be written as root 100 cancel. Okay, and let us verify this one. This is 10 by root 0.1. Okay, no need of these many steps, you verify it 0, 0. Okay, and see, V is equals to, you will get, just check it, root 5 by 2 meter per second. You verify this one, root 5 by 2, just you write this one as a 1 by 10, 10, and this you can take it as inside, and here one more 10 is there, just you check it, root 5 by 2 you will get, verify that. Okay, root 5 by 2, just verify this value, otherwise you keep as it is, no problem. What is the next one? They are asking at what distance you have to place so that this ball has to reach the box. So we need to find range. Range is equal to what? Velocity into time. Range is equals to velocity, we got root 5 by 2, verify the calculations. Time is nothing but root of 2h by g. Time, you know this one, time is root of 2h by g. Just you check this one, velocity root 5 by 2, root of 2h is 2 by 10. Okay, so you find the range. 2 comes as it other side, and root 5, root 10, 2 cancel. So you verify now, range is, you will get approximately 1 meter. This is root 5 by 2, this is 4 by 10. Okay, root A into root B, so let us write like this, 4 by 10, 5, 2 2, so R is equals to, verify this one, 1 meter. Means at a distance of 1 meter you have to place the box so that that ball has to fall in that box. Okay, here you see the formulas, how I am applying. Kinetic energy, balanced by potential energy, I got V, verify these calculations. Okay, I left here because of the time, so verify this calculation, you will get the root of 5 by 2. Otherwise you substitute this value here, nothing will happen. So velocity, time is nothing but root of 2h by g, h is clear from the diagram, g 10, take 10, and you will get 1 meter. So at a distance of 1 meter you have to place a box so that the ball has to fall in that box. Okay, so this is about some few things about spring. Okay, so in the next sessions we will enter into the power. So in work energy power, so far work is covered, energy covered, and few things about the spring also covered. Let me enter the power in the next sessions. Okay, so we will see power in the next sessions, after that some other topics. Okay, see here I am missing calculations, try to verify the calculations. Okay, calculations are your duty, you try to verify it.